This video is another in the series for Math 1224 for UTSA. Today we'll be talking about 7.2, Calculus of Parametric Curves. So we'll start with a relatively basic example, and we'll be looking at the derivatives with respect to t, as well as the derivative of y with respect to x. So given x equals t squared plus 1 and y equals 3 minus t squared, and we'll assume that t goes from negative infinity to positive infinity, find x prime of t, y prime of t, and y prime of x. So the first two are pretty straightforward. We just find the derivative. So find the derivative of this guy with respect to t. So x prime of t, this will just be 2t. Just find the derivative. Easy peasy. The next one, we just find the derivative of this guy. So y prime of t, this will be negative 2t. And I'll point out that, of course, I could call this dx dt, and I could call this dy dt if I want to use that notation, and sometimes we will. In particular, when I go to find y prime of x, the derivative of y with respect to x, I don't want to, although I could, but I don't want to eliminate the parameter and get y as a function of x. Y is a function of x in this case, but I don't want to rely on elimination of the parameter because sometimes that's really messy. So instead, I want to use the chain rule to do this. So, of course, y is some function of x, and x is, of course, a function of t. So y is a composite function, right? So if I find d dt of y of x of t, right, the derivative with respect to t, I'm finding dy dt, and that will equal, using the chain rule, dy dx times dx dt. Just chain rule, right? So what I can do is isolate dy dx by dividing dx dt on both sides. So I'll get that dy dx equals dy dt over dx dt. Okay, and that's it. That's how you find dy dx when you have a parametric system. So move that out of the way. So y prime of x, which of course is dy dx, this is basically the ratio of these two things. So this will be negative 2t, right, dy dt, over 2t. So this will be negative 1. If t is 0, well, then it depends. Of course, this reduces. We're not going to go into details about differentiability. We're not going to worry about that for the examples we're going to have to deal with. The kinds of problems that you'll be asked to do on the homework assignment aren't going to run into issues like that. Anyway, that's how you find the derivatives of a parametric system. So what's next? Oh, and I put a notice on some of these examples. I have a Desmos graph set up for these. So we're going to find the line tangent to x equals 1/2 t to the fourth, y equals t cubed minus t squared at t equals 1. Let's go ahead and look at the graph of that real quick. So here's the graph set up. I have the parameterization put in there. And if I increase t, you can see it run through the interval 0 to 2. And we go basically from the origin out to 8 comma 4. Okay, so I want the tangent line t equals 1. So if I put this here at 1, I want the tangent line right here when y equals 0, essentially 0.5 comma 0. Okay, so let's go back over here and work that out. So we'll be a little bit lazy. This is a 1/2 0, which of course you get from plugging in 1 into the two functions. Plug in 1 for t, you get 1/2. Plug in 1 for t here, you get 0, of course. So in order to find the tangent line, I need to find dy dx. So in order to find that, I need to find dx dt and dy dt. So dx dt, or of course, if I want x prime of t, if I want to write it that way, that's going to be 2t cubed, and dy dt, that's going to be 3t squared minus 2t. Minus 2t. Okay, so dy dx, this will be dy dt over dx dt. So that will be 3t squared minus 2t over 2t cubed. So now I'm going to evaluate this at 1, at t equals 1. So dy dx, evaluate at t equals 1. This will be 3 times 1 minus 2 times 1 over 2 times 1. So slope of 1/2. Okay, so y equals m times x minus x1 plus y1. So y equals the slope of 1/2 times x minus x1 is 1/2 plus 0. So we get y equals 1/2 x minus 1/4. And that should be our tangent line. Let's go take a look at the graph and confirm that that's right. So if I put in y equals 1/2 x minus 1/4, yeah, sure enough, and if I increase t there, you can see that, yeah, that is the tangent line at that point. Okay. All right, what's next? We're going to find the values of t for which x equals e to the t, y equals sine t, where t ranges from 0 to 2 pi, has a horizontal tangent line, and I have a Desmos graph for that. So let's switch to here. See, I have the parameterization here. There's actually another one here that we'll use in a different example. So if I increase t, you can see there's the graph, and we're not going to look all the way to the right. I think there might be 2 horizontal tangent lines, but definitely there's a horizontal tangent line. It looks like 3 pi over 2 is what it looks like, right? That's what we're expecting. So let's go work that out. So I need to find the derivative, so I need dy dx, so I need the 2 derivatives with respect to t. So dx dt, that's going to be, well, e to the t, right? And then dy dt, that's going to equal cosine t, right? So dy dx, this is going to be cosine t over e to the t. And we're looking for where this is either undefined or, well, we're looking for where this is 0. Sorry, I was thinking critical numbers, but no, we just want where the derivative is 0. So I want to solve this equation. Basically, I want to look for, well, where is cosine of t equal to 0 in this interval? Well, that's going to be pi over 2 and 3 pi over 2. Okay. Now, what are the x and y coordinates there, right? I found the t values, but I also kind of want to know what points those are. So for pi over 2, I'm going to have the ordered pair e to the pi over 2, comma, 1. Okay. And then for t equals 3 pi over 2, I'm going to have the ordered pair e to the 3 pi over 2, which is a bit larger of a number. Like it's about e to the 4.5 or almost 5. So pretty big number. And then comma, what would that be? -1, right? So if we go back to our graph here and I type in the ordered pair e to the pi over 2 power, comma 1, there's that point there with the horizontal tangent line. And if I do e to the 3 pi over 2, comma -1, there's going to be a point kind of far out here because e to the 3 pi over 2 is kind of a large value. There we go. So there's the other place with the horizontal tangent line. Okay. So 111-ish. But there's 2 places with a horizontal tangent line. Okay, what's next? So we're going to find the values of t for which this has a vertical tangent line. Now, for a vertical tangent line, we want to look for where dx dy is 0. Okay. The rate of change in x with respect to y is 0. Let's take a look at the graph real quick. So I'll put this one away, put those away, and bring up this one. So let's watch that run through. So it looks like, in fact, to me, that the interval starts here, but it looks to me like there would be a vertical tangent here. But let's just look for the interior. In the problem, I had written that t can be equal to 0, but let's ignore the endpoints. Let's just work with the interior. So following this, it sure looks like somewhere in here we have a vertical tangent line somewhere in here. And then I'm guessing probably there is another place somewhere pretty high up. See, the graph starts to get narrow there again, or closer to the y-axis. I'm guessing there are two. Maybe there's only one. Maybe it's just right around here. Let's go work that out. Okay, so similar to the finding dy dx, when x is some function of y, which is of course a function of t, and you apply the chain rule, dx dt is equal to dx dy times dy dt. So if I divide dy dt on both sides, I will get dx dt over dy dt equals dx dy. So it's maybe dy. So it's maybe an expected ratio to find that. So I need dx dt and dy dt. So dx dt, this is negative sine of t, and dy dt, this is e to the t. Okay, so dx dy, this will be dx dt is negative sine t over dy dt, so e to the t. I want to look for where this is 0, so essentially I'm looking for where negative sine t is 0. And of course I can multiply negative 1 on both sides, so sine t equals 0, so t will be, well, 0 of course, and then pi, and then 2 pi. At the endpoints, we are going to have vertical tangent lines, and I did include the endpoints initially, but let's ignore them. That's not very interesting. I'm more interested in this one. So I want to look at what ordered pair would that be? So if t equals pi, then what ordered pair? Well, x will be cosine of pi is negative 1, and then e to the pi power. Okay, so let's go look at that graph. So if I put in here negative 1 comma e to the pi power, there is that point right there. That's where the vertical tangent line is. Okay, what's next? So find y double prime of x given x equals t cubed, y equals the square root of t, and t is in the interval 1 to 4. Okay, so basically we need to go through the chain rule again. We said earlier that when y is a function of x, which is in turn a function of t, we can of course apply the chain rule to get dy dt equals dy dx times dx dt. And so dividing on both sides, we get dy dx equals dy dt over dx dt. Now, we can rewrite this. I'm going to strap for room, so let's do this. I can rewrite this. I'm not really changing anything. I'm just rewriting d dx of anything that's a function of x. We go through the same logic. This will be d dt of anything that's a function of t over dx dt. I'm sorry, anything that's a function of the rate of change in one thing with respect to x, but then that's a function of t dt. Okay. All I'm doing is, instead of saying that we have y specifically, we could have any function that is both a function of x and of t. That's what I'm saying. So we can plug in there, well, let's put dy dx in there. Okay. And of course here, dy dx will be a function of t. So in order to find the second derivative, we need to find the first derivative and then apply this to it. So I'm going to need, of course, dx dt and dy dt. So dx dt, this will be a 3t squared. Dy dt, this will be, well, 1/2 t to the negative 1/2 power, okay? So dy dx equals the ratio. So this will be 1/2 t to the negative 1/2 power over 3t squared. And what we're going to end up doing is we are going to find the derivative of that with respect to t. So often you will need the quotient rule for this. In this case, we don't, because these are both just power functions, so I can simplify this, but sometimes you will need the quotient rule. So this will be 1/6 t to the negative 5 halves power. Okay, so I want d dt of that. So this will be, well, negative 5 over 12 times t to the negative 7 halves power. Okay, so I've worked out the numerator here. So now I need to divide that by dx dt. So d dt of dy dx over dx dt, this will be negative 512 t to the negative 7 halves power over 3x, not x, sorry, 3t squared. So this equals negative 5 over 36 t to the negative 11 halves power. Okay? So the original question was about, yeah, just find the derivative. Okay, find the derivative as a function of x. Well, this is a function of t. I guess we could eliminate. We could say, okay, x to the 1/3 power equals t, and we can put that in, because this does say y double prime of x. So I need to plug that back in. So dy dx equals negative 5 over 36 times x to the 1/3 power to the negative 11 halves power. So I get negative 5 over 36 times x to the negative 11 over 6 power. So there we go. There's dy dx as a function of x. And really, these will usually be equivalent because x is an invertible function of t. These should always be equivalent. Oftentimes, you'll probably want to leave this as a function of t. It doesn't hurt to have your derivative as a function of t. T is the parameter, but sometimes you will probably want this as a function of x. It just depends on what we're using it for. In this case, we're not really doing anything else with this. We're just finding the second derivative. Okay, what's next? So actually here I have a little mistake. I did not put the appropriate notation here. This is supposed to be squared and squared there. So in this question, we want to find the concavity. So we will be using this for something. We're finding the concavity at t equals 1. So it's okay to have the second derivative as a function of t, not of x. And we have a Desmos graph for this. So let's go take a quick look at that. Okay, so here is the function with the parameterization. And if I increase this, we see that this makes a big loop. And we're looking for the concavity at t equals 1. And if you're paying attention, you probably noticed. So somewhere in here where t equals 1, there's some ordered pair. Now this top half is clearly concave down, and this bottom half is concave up. So you might be able to tell just from looking at it what we're going to get. But let's go back and work this out, and then we will come confirm this on the graph afterward. Okay, so basically I need to find the second derivative as a function of t. So I'm going to need dx dt and dy dt. dx dt, this will be at negative 2t. dy dt, this will equal 3t squared minus 16. Okay, so that means that dy dx equals 3t squared minus 16 over negative 2t. And I want to avoid the quotient rule, so I'm going to go ahead and rewrite this by basically dividing the denominator into the two numerators separately. So I'm going to have negative 3 over 2t plus 8t to the negative 1 power. And remember we worked out earlier that d squared y dx squared equals d dt of dy dx over dx dt. Okay. So I need the derivative with respect to time here. So d dt of dy dx equals, that's negative 3 over 2 minus 8t to the negative 2 power. Okay. Then I need to divide that by dx dt, this guy. So d2y dx squared equals -3/2 minus 8 to the negative 8t to the minus 2 power divided by -2t. And again, just to simplify things, I will divide the denominator into the two numerators. So I'll get 3/4 t to the -1 power plus 4t to the -3 power. So there we go. That is the derivative as a function of t. And I want to find the concavity at t equals 1, so I'll plug 1 in. So d2y over dx squared. Evaluate at t equals 1. This will be, well, 3/4 times 1, right? Plus 4 times 1, which is positive. So we get concave up, right? So let's go check this in the graph. If we back up the parameter to where t equals 1, here, yeah, you can see that this is concave up, right? Based on that section. If you focus in on this point, and I guess that was what, 3 minus 15 there. And if I complete the rest of the graph, you see, yeah, that's concave up for sure, right? Okay. All right, so what's next? So we're going to find the area under this curve. When I say under, I mean in the sense we have done before with the area under a curve, between that curve and the x-axis. Under is maybe not the best wording here, but hopefully that's pretty clear. So, and we have a Desmos graph to go with this. So basically, this can be fairly straightforward or not so straightforward. So the uh, the the book does go through some details in the Riemann sum, and it's not overly complicated, but I think what we're going to do is just skip all the Riemann sums for this and the other examples. We're going to do arc length and surface area as well. And I don't certainly want to do all the Riemann sums. And this one, it's not that it's particularly difficult, it's just tedious. So maybe we'll leave that for another video. I'm just going to show you the most straightforward way to do this. And it's actually relatively simple. Let's first go look at the Desmos graph, though. So let's switch that. So here is, this is actually the same graph as one of the previous examples. And here is sine, this e in sine. This is one we did earlier. So if we're going up to t equals pi, then actually, let's do that. That's good enough. And actually, this is an intercept here, right? But it's not perfect because we're stopping at 3.16, but you get the idea. So we're basically looking for this area right here. What's the area under that graph? Okay. And if we were to try to eliminate the parameter, we could, but this would be fairly complicated. We would basically have, if we eliminated the parameter, we would have something like this. We could say, oh, I can just rewrite this as ln of x equals t and plug that in and get y equals sine of ln of x, right? And then try to integrate that. Maybe you can see the problem with trying to integrate that. So that's not what we're going to do. We're going to do something related but different. Obviously, since we saw from the graph that y is a function of x. We don't have the graph passes the vertical line test, right? So I should be able to say, okay, well, I'm going to integrate from x of 0 to x of pi, right? Those would be the x coordinates. Y times dx, the height of each rectangle times the width of each rectangle. And that should work fine, right? Well, all we have to do is do a change of variable using this substitution, x equals e to the t, so that dx equals e to the t dt, and then y is sine of t. So, crowding myself here. So this equals the integral from 0 to pi of sine t times e to the t dt. And all we got to do is calculate that integral, and we will find the area. Now, this one's not so straightforward. This one's a bit complicated. We're going to have to do integration by parts with, I believe, 2 steps for this one. So it isn't exactly easy, but it's just an integral that we know how to do. So let's get started. So I'm going to say that this is my u, this is my v, okay? So this will be sine t times e to the t, because the antiderivative of e to the t is, dv. E to the t, because the antiderivative of e to the t is e to the t, evaluated at 0 and pi. And this, you might notice right away what's going to happen here, but we'll see that in a second. Minus the integral from 0 to pi of v, which is e to the t, times du. So cosine t dt, all right? If we evaluate this guy, sine of pi is 0, sine of 0 is 0. So this whole thing is 0, conveniently. So we get 0 minus, now here, I'm going to rearrange this. I'm going to pair the e to the t with the dt, because we have to do integration by parts again. So this will be the integral from 0 to pi of cosine of t times e to the t dt, okay? I'm going to call this w. I don't want to reuse u. We've already used it up here. And this is dv again, okay? So this will equal, I can drop the 0, minus cosine t times e to the t, evaluate at 0 and at pi, minus the integral from 0 to pi of e to the t times negative sine t dt. Okay? So now I'll distribute this minus sign onto this term and this term. And notice that in the second case, we're going to have 3 minus signs. So we're going to have this group here minus this 1 minus sign for that second term. So we're going to get, and we'll evaluate later, cosine t times e to the t from 0 to pi minus the integral, and I'll rearrange the order a little bit, sine t e to the t dt. And you might notice, hey, wait a minute, this is what we started with up here. So, and hopefully you remember this, we've done this before. So this is the integral. Oh, I forgot my limits. 0 pi. Sorry. So this is the integral from 0 to pi of the thing we started with equals this thing we just got. Okay, now I can add this on both sides. So I will have 2 times the integral from 0 to pi sine t e to the t dt equals cosine, and we'll do the evaluation soon, and from 0 to pi. And we'll divide by 2 on both sides. So the integral from 0 to pi, the area that we're finding of sine t e to the t dt, this equals 1/2 times, let's go and do the evaluation now. Cosine of pi is -1 times e to the pi minus, oh, you know what I did? So I forgot. I talked all about this minus sign being applied, and I did it correctly here, but I didn't apply it here. So I'm missing a minus sign. So let's go put those back in. So it's going to go here, and here, and here, and here. So minus, 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 minus. Okay. So here we'll evaluate it 0. So 1, cosine of 0 is 1 times e to the 0. Okay. So this equals -1/2 times, well, negative e to the pi minus 1. So 1/2 e to the pi plus 1. So that is the area that we were looking for. Okay. And this is approximately, do I have a decimal approximation? I do, 12.070. Okay. Now, if you try to you have Desmos find this area for you, it doesn't know how to handle. We can't just switch to Desmos and have it confirm the number for us, because it doesn't know how to handle areas under parametric curves unless you do the work and you give it. If you were to give Desmos this, it would calculate the 12.0704 if you wanted to do it that way. If you wanted to check your answer, of course. But you have to go through this technique to figure it out. Anyway, what's next? This one. So this one, and we have a Desmos graph. This one I really like. So let's go look at the graph. So here's y equals sine of x plus y. And you can notice, hey, this is a function. Y is a function of x. This passes the vertical line test. So, and it's continuous. So this function should be integrable. So we should be able to find the area between the curve and the x-axis from 0 to pi. If I try to say, okay, Desmos, give me the int from 0 to pi of, well, the problem is, how do you get y as a function of x here? How do you solve for y? And the short answer is, I'm not sure that you can. Y is a function of x, but how do you find a closed form for it? Well, it turns out that there is a parameterization we can use. So let's switch back to this and figure out the parameterization. This takes a little bit of cleverness. It's not so obvious. If you try to say, oh, x equals t, that won't do you any good. So for this one, what you have to do is the following. I'm going to say that t is this whole inside part. Okay, so x plus y equals t, and y equals sine of t. All right, so here I can subtract y on both sides. X equals t minus y, but y is sine of t. So x equals t minus sine of t, and y equals sine of t. So this is a parameterization of this curve, okay? Now, what interval should we use? Well, x goes from 0 to pi, right? Well, if you think about it, what would you put in here to get 0? Well, if you plug in 0, you get 0. 0 minus sine of 0 is 0. What would you plug in to get pi? Well, if you plug in pi, you'd have pi minus sine of pi. And sine of pi is 0. So you'd have pi minus 0. So you get pi. So we're going to let t go from 0 to pi. So we do have the same interval. That's convenient. So now if we use this parameterization to find the area, we will get the area of this other curve. But let's go check the graph real quick to make sure this looks right. So here's the parameterization, t minus sine of t, comma sine of t, right? As I increase capital T, in fact, let's do it this way. You can, the Desmos handle, you can see that, yeah, that traces out the graph of, well, the graph. I mean, it's a function. Y is a function of x. It passes the vertical line test, but how do you get a closed form for that? That's not so simple. So we can use a parameterization instead. So I'm going to want to do the integral from 0 to pi of y times dx, right? That's how we find area just in general. So I'm going to need to find dx. So dx equals 1 minus sine, 1 minus cosine of t dt. Okay. And again, the change of variable, the interval is the same, so that's convenient for us. So this equals the integral from 0 to pi of sine of t times 1 minus cosine of t dt. Right? So it's an integral that we know how to deal with. And you might think, oh, this is going to be messy. But actually, it's pretty straightforward. If we do the substitution, v equals 1 minus cosine t, okay, then dv equals, well, sine of t dt. Hey, we already have a sine right here. So if I just reorganize a little bit, I'll have the integral from 0 to pi of 1 minus cosine t times sine of t dt. Hey, that's dv, that's v. This is turning out to be relatively simple. So my new limits of integration for the substitution, if I plug in 0, I get 1 minus 1, so I get 0. If I plug in pi, I get 1 minus negative 1, so I get 2. So the integral from 0 to 2 of v dv, so that equals 1/2 v squared from 0 to 2. So that will be 4 over 2 minus 0. So 2 is that area. So let's go look at the graph of that. So there's no good way to get Desmos to shade this in for you and have it calculate 2 for you, because you'd have to have y equals f of x. And there's not really a good way to do that. But what I can do, which might be convincing, is go over here and I'm going to put an additional parameter in front of a multiplier for a, so that if you slide a around, you get different, you're forcing this to lean. And if you make a equals 0, then you just have y equals sine of x, because a is 0. And this is just the sine function, right? And I didn't put down here the parameterization. Let's not worry about that. Now, if you do the area under the sine function from 0 to pi, you get 2. And that's something you can do just normally, Cal 1 stuff. And indeed, Desmos will do that for you. If you do int 0 to pi of sine of x dx, it will give you 2, right? Now, when you slide this horizontally, that does not change the area, it turns out. So if you were to go redo this with, say, a equals negative 0.7, so if you did y equals sine of x minus 0.7 y, you could do the whole thing all over again, and you should get 2 again. So maybe that's helpful to see that this is one you can do with Cal 1 techniques, and you can get 2. Desmos will give you 2. But if you do some shearing on these, the area is not affected, which to me, it's pretty interesting. So let's go see what's next. Okay, so length, arc length. So you might recall that when you have y equals f of x, then you can find arc length in the following way. This equals integral from a to b of the square root of 1 plus dy dx squared dx. Okay. I'm going to skip the details, much like with finding the area under a curve. And I'm just going to give you, if you have a parameterization, how do you find this? So for a parameterization, or for a parametric curve, L will be the integral from t0 to t1, whatever your interval is, which I guess I could call a and b, of the square root of dx dt squared plus dy dt squared dt. Okay, and again, the reasons are not super difficult; they're just tedious. Let's skip that. So I'm going to need dx dt and dy dt. Well, dx dt, that's not hard. That's just negative sign, right? And then dy dt, that's also not hard. That's just cosine of t. So we're going to get the integral from 0 to pi over 2, okay, of the square root of negative sine t squared plus cosine t squared dt. Okay. Now you might recognize, oh, this is just 1, right? Sine squared plus cosine squared is 1. So we have the integral from 0 to pi over 2 of 1 dt. So this will be t evaluated at 0 and pi over 2, which will be pi over 2 minus 0, which is, of course, pi over 2. And you might recognize, if you wanted to confirm this, we don't have a graph here, but this just makes a circle of radius 1, and this interval represents going a quarter way around the circle from 1 comma 0 going counterclockwise. So that's a quarter way around the circle of radius 1. So well, a couple ways to think about it. One's the circumference would be 2 pi, right? So the arc length would be 1/4 of that, because it's a quarter way around, so pi over 2. So we worked a relatively simple example, but you can see that, yeah, this formula seems to work. Let's do one that's a little bit more complicated. So we're going to find the length of x equals t squared minus 1, y equals t cubed minus 1 on the interval 0 to 1. I don't have a graph of this, but if you want, you can always make the graph yourself. So I'm going to need dx dt. So that's going to be 2t, and I'm going to need dy dt. That's going to be 3t squared. I'm going to need their squares. which I guess I'll sort of front load this and do this up front. So y, or rather 4t squared, and then dy dt squared, so 9 t to the 4th. Okay, so we want the integral from 0 to 1 of the square root of 4t squared plus 9 t to the 4th dt. And this might look really bad, but don't worry, it's going to be fine. So the first thing I notice is I can do some factoring inside. I probably have lots of vertical room, but I'll go ahead and utilize some horizontal room as well. So this will be the integral from 0 to 1 of the square root of t squared times 4 plus 9t squared. Got a little overzealous there. dt. Okay. Now, this guy can come outside, and I don't need an absolute value because everything is non-negative anyway. If you were to bring this t squared outside of the root, it would become absolute value of t, but there's no negatives anyway, so I don't have to do that. So this will be the integral from 0 to 1 t times the square root of 4 plus 9t squared dt. So I'm going to do a change of variable. I'll say that u equals 4 plus 9t squared. So du equals 18t dt. Okay, so I'm going to need to borrow an 18. So this will be 1 over 18, integral from 0 to 1 of 4 plus 9t squared to the 1/2 power times 18t dt. And then I will go and do my substitution. So 1 over 18, plugging in 0 for u, I'll get 4. And plugging in 1, I'll get 13. U to the 1/2 power du. Okay, so this will be, well, 1/18 times 2/3, so 1 over 27. U to the 3/2 power, evaluated at 4 and 13. So I'll get 1 over 27 times, well, 13 to the 3/2 power, I guess, which we could write differently, which I may do. 1 over 27 times 13 root 13, if you want to write it that way, minus 8. There we go. That is the arc length. I don't have a graph, but you could check that yourself. You could look at it yourself if you want. Okay, what's next? So find the area of the surface generated by revolving the curve x equals t squared minus 1, y equals t cubed plus 1/3 t from 0 to 1 about the x-axis. And I don't have a graph for this one. Okay, so basically I chose this one carefully. This 1/3 is kind of important so that it works out relatively easily. If you just pick random ones, the integral you end up doing might be kind of a pain. You might recall when you have y equals f of x, right, is some function, and f of x is greater than or equal to 0, right? This function doesn't cross the x-axis. Then the surface area, this would be the integral from a to b of, well, actually, 2 pi times the integral from a to b of y times the square root of 1 plus dy dx squared dx. In other words, this is called ds, right? The differential of the arc length. If you have a different orientation and you're revolving around the y-axis, then here you would have x instead of y, but it just whatever variable you are not revolving around, basically. So we get a similar thing. Basically, we're going to do this. We're going to do, for the parametrized curve, we're going to have the surface area is going to be 2 pi times the integral from t0 to t1, which I guess I could call a and b, of y, whatever that function is, y of t if you want, times the square root of dx dt squared plus dy dt squared dt. Okay, so I'm going to need dx dt and dy dt. So I guess I will do this. Give myself a little more room. So this will be 2t, then dy dt. This will be 3t squared plus 1/3. Okay, so this will be 2 pi times integral from 0 to 1. And I'm probably going to try to give myself some horizontal room as well. Well, y is t cubed plus 1/3 t times the square root of this squared, so 4t squared, plus this squared, okay? So 9t squared, fourth rather, plus 2t squared plus 1/9 dt, okay? Checking my foiling is right. I believe it is. I can combine like terms here. I've got 2 quadratic terms in the radical. So this will be 2 pi times integral from 0 to 1 of t cubed plus 1/3 t times the square root of 9t to the 4th plus 6t squared plus 1/9 dt. And this might look really bad, but like I said, the numbers were chosen carefully. The coefficients were chosen carefully, so this wouldn't be that bad. Basically, we're going to do the most obvious substitution. We're going to say that u equals the radicand, okay? U equals 9t to the 4th plus 6t squared plus 1/9. So du equals 36t plus 12t dt, okay? So I'm going to need to borrow. Notice that this is a multiple of this, a multiple by 36, right? 36 times this guy gives you this guy. So I'm going to need to borrow a 36. So this will be, well, 2 pi over 36, so I have to borrow it, integral from 0 to 1, of 9t to the 4th plus 6t squared plus 1/9 to the 1/2 power times 36 times t cubed plus 1/3 t dt. So here is my u in here, and here is my du. So this will be pi over 18 times the integral from 0, well, hold on, from 1/9 to, I believe it's 126 ninths. Let's double check. If I plug 1 into here, I'll have 9 plus 6 plus 1/9. So I'll have 15 plus 1/9. Yeah, 15 times 9 is 135. So 136 over 9. Okay. U to the 1/2 du. Pi over 18 times 2/3 times u to the 3/2 power evaluated at 1/9 and 136 over 9. It's getting a bit messy with the fractions, but the substitution worked out pretty well, I think. So pi over 27 times, well, 136 over 9 to the 3/2 power minus 1 over 9 to the 3/2 power. If I want to simplify this a little bit, I could say this is pi over 27 times 136 root 136 over 1 over 27, or rather, over 27, I mean to say, minus 1 over 27. So clean this up a little bit more. I get pi over 729 times 136 times root 136 minus 1, and just a little bit more. Maybe this is overkill. Pi over 729. 136 is 4 times 34. So this will be 272 times the square root of 34 minus 1, which I love arithmetic, but there we go. That's it. That is the surface area you get by revolving this parametric curve around the x-axis. What's next? Well, I have a blank page here because I wasn't sure how long this would take. Here's another example. Now, this video is plenty long, so we're not going to work this one out. But this one you can do, so I'd encourage you to work this one out. The substitutions get a little spicy. It would add a bit of length to the video, but I've given you the pieces, the components to deal with this one. We found the area under this curve, and we did an example of finding surface area. So you should be able to work this one out. It just would be a little tedious, but I encourage you to try this one.